Okay, we're going to continue on here, chapter 3, talking about bonding. We talked about bonding last time, and we talked about drawing Lewis structures for covalent compounds. Remember that when you draw Lewis structures for covalent compounds, it's a really good idea to sort of follow certain steps that we talked about. Really, one of the first steps is to figure out the total number of valence electrons. Remember that you should think of the valence electrons as the number of electrons you need to distribute throughout the entire molecule, not necessarily belonging to anybody in particular, but just there to kind of distribute. You want to think about logical arrangement or the skeletal structure. Remember that it's usually the least electronegative atom that occupies the center spot. So fluorine should never really be in there. Hydrogen, because it should only have basically one bond, should never find itself in there. In most cases, though, as we did talk about, if you have like one element and maybe 3 or so of some different elements that are the same, usually the one sort of elements in the middle, everything's sort of attached to it. Next thing you want to do is really just make one single bond from the center to the outside atoms. That will use up a certain number of electrons from your total. However many electrons are left over at that point will go on the outside atoms in pairs. Which are basically dots, until you complete the octet on the outside, except obviously if it is hydrogen, then you would not obviously put any dots on hydrogen. If you sort of make single bonds, put all your dots on the outside atoms, and you still have electrons to put onto the atom, then you go to the center atom at that point and also put them on as dots. At that point, you should hopefully be out of dots and electrons, I hope. And the last thing you want to do is make sure that everybody has met the octet rule. Obviously, except for hydrogen, this should only have 2. And it's at that point, really, if somebody does not meet the octet rule, that you might want to apply a double bond or a triple bond if necessary to sort of fix that. And remember, when we make double bonds or triple bonds, we're basically bringing electrons in to do so. And we're not adding electrons, otherwise we'll have too many on our total. At that point, really, you want to kind of exhaust all your double bond opportunities. And if you do exhaust your double bond opportunities and they're still don't have enough electrons, then you should move to a triple bond. So in most cases, as we might have talked about, you don't really want to kind of double bond or triple bond right out of the box. You usually want to kind of save that for some way to fix an issue that might come up. The other thing that we sort of talked about as well is formal charge. And the formal charge, basically the charge that the atom sort of takes on in the arrangement is bound to. So the formal charge is equal to the number of valence electrons in the free atom minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. So what this will give you is basically the charge that that atom has in that orientation. It'll also account for, the overall charge, if it is an ion or something like that, sort of where the charge is lying in that particular sort of compound. We talked also about really the 3 types of bonds that we come across. Remember, an ionic bond is always between a metal and a non-metal, where we have a complete transfer of electrons from the metal to the non-metal. On the other end of the extreme, we have our non-polar covalent bond, which is usually between 2 non-metals, where we have equal sharing of electrons. And in the middle of those two is also a covalent bond, but that is a polar covalent bond where we have unequal sharing of electrons between the two. The result of that unequal sharing of electrons basically means that we do end up with a partially positive side of the bond and a partially negative side of the bond. That results in that. A nonpolar bond could kind of be considered like a neutral bond, if you will. There's no side that's more positive or more negative in there. Any questions on any of that stuff there? Yeah. Yeah, so it's basically the number of valence electrons in the free atom. So like you would go to the periodic table and go, carbon's got 4, minus the number of non-bonding electrons. So these are actually individual electrons. So actually each dot counts. So, 2, 4, 6, 8, all the dots that you have in your picture, minus 1/2 the number of bonding electrons, also each individual dots, basically. Yeah, as well. Yeah. It tells you basically the charge that that atom is basically taking on in that sort of arrangement, how it's bonded and sharing electrons. So for example, we think of things having certain charges when they either gain or lose electrons. But when they're sharing electrons, sometimes elements take on different types of sort of charges because they're sharing electrons with other elements that are there. And really depending on sort of electronegativity of all the other elements that are there as well, it may give a element that you normally think of as like, it's usually always like -1, may actually end up taking maybe like a positive sort of charge in that situation, or maybe a -2 charge in that situation. Other questions or yeah? How would so what happens in the case of sort of the two types of bonding is we're not really turning necessarily one element into another. What we're doing is making that element have kind of the same electron configuration as like the noble gases, which is group 8. So in an ionic compound, the way that's achieved between a metal and a non-metal, and also because of those periodic trends we talked about, the metals will lose electrons, and that allows it not really to change elements, but it allows that particular element to end up with the same electron configuration as the noble gas that came right before it. So it makes it a little bit more stable. And non-metals will gain those electrons, and what that does in an ionic compound is it allows it to go forward. Again, not really changing elements, but becoming really the same as a noble gas in terms of its electrons and becoming really stable. In covalent bonding, there isn't a complete transfer of electrons. So how these elements basically achieve that kind of noble gas configuration is through sharing electrons, which is why technically we want everybody to kind of share 8 electrons, which gives it really the same electron configuration as noble gases and makes for a very stable sort of bond, except for hydrogen, which again, if you look at hydrogen, the next noble gas past hydrogen is helium. And that's why, again, hydrogen just needs 2 electrons. It just needs to get over there to really helium's configuration in terms of electrons to become really stable. Is that your question? Yeah. Okay. Other questions? Okay. So we left off talking about formal charge. So let us continue and talk a little bit more about formal charge here. So why don't we try one here? So this is ozone. So why don't you take a couple of minutes and calculate the formal charge on each of the oxygens. So calculate the formal charge on each oxygen here. Okay, let's take a look here. So we'll start with the double bonded oxygen. Like something like that. So the formal charge here for this oxygen would be oxygen, which is group 6. So it'll be 6 valence electrons, minus in this case 2 and 4 non-bonding electrons, minus 1/2. Each line represents 2 electrons. So that's 2 and 4. That gives me 6 minus 4 is 2, minus 1/2 of 4 is 2, which means it is 0. So the formal charge on the oxygen over there would have a 0 formal charge. If we did the single bonded oxygen, look something like this. The formal charge here would be 6 minus 2, 4, 6 minus 1/2 of our line there, which would represent 2 electrons. That's going to be 6 minus 6 is 0, minus 1/2 of 2 gives us a -1. So in this arrangement here, the oxygen on the right there has a -1 sort of charge associated with it. And lastly, if we look at the oxygen in the center, which is kind of a double bonded oxygen with a couple of dots and a single bond coming out the other side, that's going to give us the formal charge here, 6 minus 2 minus 1/2 of 2, 4, and 6 electrons. That's 6 minus 2, which is 4, minus 1/2 of 6, which is 3. So that is 4 minus 3, basically, which is +1. So the oxygen there in the center takes on an H. Now the oxygen in the center takes on a +1 sort of formal charge in this sense. When we add up all the formal charges, we do end up with 0. So that's good in that sense. And that is the formal charge on each of these oxygens here. Yeah.
Have all the formal charges and out your overall charge?
Yeah, so that basically is sort of where the overall charge sort of lies when you calculate the formal charge. The formal charges should add up to the overall charge. So if it's neutral, like in this case, they should add up to 0. And obviously, if it has a charge, they should add up to that charge. Yeah. Exactly, it would add up to that. Yep. Other questions? Okay. So why don't we do carbonate, which we drew earlier? So why don't you calculate the formal charge on all those? Okay, let's take a look here. So we'll start with our double bonded oxygen, which, by the way, will turn out the same here. So our formal charge will be 6 minus 4 minus 1/2 of our 2 bonds, which is 4 electrons. And that is 6 minus 4, which is 2, minus 1/2 of 4, which is 2 as well. So that's going to give us 0. So this guy is 0. Our oxygen that's single bonded here, once again, would be 6 minus 2, 4, and 6, minus 1/2 of 2, going to be -1. The guy on the left there will be exactly the same. And if we do our carbon in this case, it looks something like this. Formal charge of carbon would be 4 minus 0, minus 1/2 of 8 electrons, gives us 0. This guy's, yeah. So in this particular case here, to kind of answer your question as well, we see that the -2 adds up. And in this case, the -2 is really revolving around those oxygens that are single bonded, is where sort of the charge in this particular ion comes from. Any questions on that there? Now, as we talked about, I think at the very end last time, we can use formal charge to help us decide between a couple of different structures as to maybe what Lewis structure might be a better one versus another. Sometimes you can draw sort of an acceptable structure, Lewis structure, but sometimes, based on formal charge, there's sort of maybe a better structure that you can draw. So sometimes you'll be asked, or you'll see questions where they'll say, based on formal charge, draw the best sort of structure that you can. So we can use this to help us decide between different structures. For neutral molecules, and just in general, if you pretty much could minimize the formal charge to 0, that is pretty much ideal, or at least most of it to 0 is usually a pretty ideal sort of situation. Lewis structures with really sort of larger sort of formal charges, 2s and 3s, are probably less plausible to occur. And when sort of choosing among different Lewis structures that have sort of a similar distribution of charge, like a -1 +1 distribution, you do want to sort of have the more negative formal charge on the more electronegative atom. And that makes sense for the idea that it's more electronegative. It ideally should be drawing electrons towards itself. So in a probably best structure situation, it should be more of a negative charge than, say, a positive charge because of that. So we can use these to help us decide between different structures. So why don't we try this here? Here's a couple of structures for formaldehyde, using formal charts to decide which one is the better structure, and when we also do between these two carbon dioxide for our people that like to triple bond everything. Decide between those two based on formal charge, which one is better. Let's take a couple minutes to see what you come up with here. We'll start with the guy on the left here. We'll do our single bonded hydrogen. So our single bond hydrogen here, the formal charge would be 1 minus 0 minus 1/2 of 2 gives me 0. This hydrogen is exactly the same, so it should be carrying a 0 as well. We can go to the carbon there in the middle that has like a double bond action sort of happening. Formal charge here would be 4 minus 2 minus 1/2 of our bonds, which is 2, 4, and 6. That gives me 4 minus 2, which is 2, minus 1/2 of 3. So that would be 3. So it's going to be a -1 if I did that math right there. In that case. And lastly, our oxygen here that looks double bonded like so. And that would be formal charge is 6 minus 2 minus 1/2 of our 3. So that is 6 minus 2, which is 4. 3, the 6. There we go. Minus 3. So that's going to be +1 in this case here. Yeah. Any questions on that? By the way, instead of doing half the number of bonding electrons, you could just count the bonds, and that works the same way, obviously, as well, which is what I kind of did there. Yeah. All right, we'll go to the guy on the right here. Our hydrogen is going to come out the same. So that's going to be, once again, our 1 minus 0 minus 1/2 of 2, which would be 0. So that is 0. That is 0. Our double bonded oxygen, as we did previously, will also come out the same. So 6 minus 4 minus 1/2 of 4 going to get you 0. And lastly, our carbon in the middle there that looks something like that will be 4 minus 0 minus 1/2 of 8, which would also be 0 in this case. So based on formal charge here, the better structure is the one on the right. That's pretty much minimized all formal charges to 0. So that is a good deal. This has not too bad formal charges, but when comparing this element to that element, carbon and oxygen, the one that's more electronegative is which one? Is the oxygen. And in this arrangement, the oxygen actually has the more positive formal charge, which also is not a great deal. It's a good situation in that case. Any questions on that there? Yeah, so again, the idea there is if you have a distribution like that where like +1, -1, you would want the more negative one to be on the more electronegative because of that, because it should be dragging electrons towards itself and becoming kind of more negative in that situation. Other questions? All right, so rolling to our carbon dioxide. We'll do our single bonded oxygen there on the guy on the bottom. That's going to be 6 minus 6 minus 1/2 of 2. That is going to be a -1 for this guy. Our triple bonded oxygen, rarely seen, is 6 minus 2 minus 1/2 of 6. So that's 6 minus 2 is 4, and 4 minus 3 is +1 in this case. And now our carbon, which looks something like that, would be 4 minus 0 minus 1/2 of 8, which would be 0 in this case. So on that guy on the bottom, we have -1 on the oxygen on the left, +1 on the oxygen on the right, and 0 for the carbon in the middle. Our double bonded oxygen here will end up at 0 and 0, just like we did down here at wherever that calculation was. We did that. Should be this one. And our double bonded carbon in each side there would be 4 minus 0 minus 1/2 of 8, which would also be 0. So once again here, this is really based on formal charge, the better structure for CO2 as it minimizes formal charge down to zeros, even though triple bonds look cool, but not so good in this situation. Yeah. Any questions on any of that there? So again, this is a situation where if you are asked a question to draw the best sort of structure, Lewis structure based on formal charge, you know, you could try a couple of different arrangements and sort of see, you know, is this one arrangement better than the other based on formal charge? If it frankly doesn't ask you to draw your Lewis structures, best one based on formal charge, you technically lay up any type of structure that is sort of following those rules that we talked about, you know, a little bit earlier, is the best idea there. So for example, we drew a little nitric acid, I think earlier, like something like this. So, you know, if you felt like, hey, maybe I just want to do a different sort of nitric acid move and I like to put my oxygen there in the center, why not? Feels good there. And maybe throw my nitrogen on the outside as well. Do a little bit of that. And go, hey, I think I like that structure better. So we could look at the one we drew here on the left, which was the original one that we drew. And again, the formal charge here on this guy would end up -1 like we did previously. This guy would end up at 0. Our oxygen there that looks like this will be 6 minus 4 minus 1/2 of 4, which will also be 0. Our hydrogen will be 0. And our nitrogen here, which is sort of double bonded that way, will be 5 minus 0 minus 1/2 of 8 will be +1. So we end up with a +1 sort of action happening there. Now our nicely funky nitric acid over here, this guy will end up at -1. This guy will end up at 0. That will end up at 0. The oxygen there that's double bonded and single bonded will be 6 minus 0 minus 1/2 of 8. That's going to give us basically a -2, I believe, if I'm doing the math there. That is actually, no, it is +2. There we go. So give us a +2 in that case. And then for our nitrogen, something like that would be 5 minus 4 minus 1/2 of 4 gives us 5 minus 4, which is 1. And 1 minus 2 is going to give us -1 in this case. Yeah. Which one would be better? The better structure would be the guy on the left here, right? Mostly zeros. The advantage of the guy on the left is between nitrogen and oxygen, they're both 1s, right? The more electronegative element between nitrogen and oxygen is oxygen, and the guy on the left is carrying a -1 charge, right? The more negative formal charge, so that's good. Over here, we got a lot of zeros, but we do have a pretty high positive formal charge, which is not so great. And when we look at, for example, our nitrogen here, between our nitrogen and our oxygen in the center, the nitrogen, which again is the least electronegative in this case, is actually carrying the more negative charge between that and the oxygen in the center, which is a +2. And that's also not so great. So again, you could use these to help you reason, you know, what structure would be good or bad. Also why in certain cases we attach things kind of the way we do, so that we get our correct sort of arrangement. Also why this would be a crappy acid, because frankly, that hydrogen will not go anywhere probably in that case, will not come off or anything. So probably hang on a lot more than it would on the left. All right, any questions on formal charge, how to use it? All right. So we talked a little bit about resonance, but let's talk a little bit of bond length. Bond length is really the distance between the two nuclei that are in a bond. You do not need to obviously memorize any of these numbers, but we do see a pattern when we look at, for example, the carbon-carbon single bond, double bond, and triple bond. The bond length for their single bond is 154, 133, and 120. If we look at the carbon-nitrogen single, double, and triple bond, Goes from 143, 138, 116. What we see is single bond is longer than a double bond, and a double bond is longer than a triple bond. So essentially, every time you bring those electrons in to make the double bond, brings everybody closer. Triple bond bringing electrons in, going to bring everybody closer to each other. Now, that's really important because that obviously does relate to bond strength. And the bond strength is pretty much that pattern. A triple bond is much stronger than a double bond, and a double bond stronger than a single bond. I equate it to like a brand new pencil out of the box. It's nice and long. You could take that thing and snap it, no problem. You take that pencil, take a couple chemistry tests, you're left with an eraser and a nubbin, right? Like that big, very, very hard to try to break. And it's sort of the same way with our bonds here. A double bond is not like twice as strong as a single bond or anything like that, but that's the general pattern that we do see. All right, so we talked about electronegativity. Still goes this way and that way, and we talked about that earlier. We talked about bond polarity. So let's talk a little bit about dipole moments, and specifically for a specific type of molecule, and that is a diatomic molecule. And a diatomic molecule obviously is what it sounds like. It is only two atoms involved. And remember that when we use electronegativity, we're really measuring what is referred to as sort of bond polarity. And if you remember, that electronegativity scale is that scale that goes from like 0 to 4, where you subtract the numbers. And if you hit something like 0 to 0.4, that's a non-polar bond, right? The difference in electronegativity. Above 0.4 to below 2 is a polar bond. And remember, basically above 2 in most cases, but not all cases, is an ionic bond. And as we talked about, you really don't need the numbers for that. As if it's a metal and a non-metal, it will be an ionic bond. So, you know, that's what it is. The only place really that bond polarity, where you use electronegativity values, and molecular polarity, which is really what a dipole moment is, crossover and are really the same thing, is when you're dealing with diatomic molecules. And that's because in a diatomic molecule, how many bonds are there? It's just one, yeah, between the two atoms, basically. So if that bond is polar, then the molecule will be polar. And if that bond is nonpolar, then that molecule will be nonpolar, because it's the only bond in the entire guy. So if we had something like our fluorine here that we saw earlier, or even our oxygen, or even our nitrogen, doesn't matter if it's double bonded, single bonded, or triple bond. In all these cases here, if I did the difference in electronegativity, that's a big 0, 0, and 0 difference between those two, as they're all both the same element. They have the same value, right? So 4 minus 4 is 0, and so forth. That means that this bond here, here, and here, they're all non-polar bonds. And once again, because this molecule only contains that bond, that means that these molecules are also non-polar molecules. Non-polar molecules overall share electrons equally, and in the entire molecule, which in this case is just the one bond, it does not have a dipole moment. So a dipole moment only occurs in polar molecules. And so nonpolar molecules, obviously, because there's equal sharing electrons, do not have dipole moments. But if we do some like we've seen before, like HF, you know, HCl, and so forth, these are now going to be polar bonds. The difference in electronegativity here is something like 1.9, which means that this bond is polar. If we drew our dipole arrow, it should be pointing towards which element? Be pointing towards fluorine. Yes, that is the more electronegative element there. And what that means in terms of our HF, once again, is the fluorine takes on a partially negative bond and a partially positive sort of charge there on the hydrogen. This arrow that we drew for this particular bond is the bond dipole arrow, and that would also be the dipole moment. Yes, where the fluorine side of that molecule is going to be more negative, hydrogen side of that molecule is going to be more positive. And once again, we could safely do that because frankly, there's just one bond and we don't have to worry about it. In the next chapter, we'll talk about what happens when we deal with guys that have multiple atoms involved, 3 or more atoms. You have to take a couple of things into account. You have to take into account the geometry of the molecule and are there polar bonds. So the simplest ones to figure out is the molecule polar, the molecular polarity is diatomic molecules. All you have to do is identify, is that bond the only bond there, polar or non-polar? If it's non-polar, it's a non-polar molecule. If it's a polar bond, it is going to be a polar molecule. Any questions on that there? We will not calculate anything like that, so you don't have to worry about the charge and the coulombs on it. Yes, yeah. Yeah, so in most cases, if this is your question, in most cases, the way that you would represent a dipole moment is to use that arrow. And for example, in this one, we would point the arrow going that way, which means the dipole moment's heading towards the fluorine being more negative and stuff like that. In the next chapter, we'll talk about things with multiple sort of more than three or more atoms involved. Water is a polar molecule, as we may know. You would draw it basically like this. The individual bond between hydrogen and oxygen is a polar bond. And those would be the bond dipoles. They actually add to each other, as we'll talk about when we get there. And they create an overall dipole moment in water that is heading in that direction where the oxygen is more negative and the hydrogen side is more positive. So individually, when we get to 3 or more atoms, the overall dipole moment is really a combination of the individual bond dipoles and the geometry that's there. That's just sort of which way the arrow would point and actually how big the arrow would be as well if you actually did the calculation. So sometimes the arrow is big, sometimes the arrow is small to indicate a big sort of dipole moment. But in the case of water, for example, the overall dipole moment would actually be represented by that sort of, I don't know if you can see the red arrow there, but the red arrow in the middle would represent the dipole moment. The individual arrows on the side would represent the bond dipoles, the individual bond dipoles, which you would use difference in electronegativity to figure that out. The why is so simplified here in a diatomic molecule is, again, there's just one bond. So basically, whichever way, that's, you can only basically put 2 things in a straight line. So you'll just have an arrow pointing in one way or the other when it's diatomic. So both the bond dipole and the dipole moment will be basically the same arrow. Other questions? And as you can see here, chlorine has no dipole moment, as it would basically have equal sharing of electrons. Then we have some dipole moments. And then this is a super dipole moment there. And so much so that, as we know, there's really no sharing of electrons. They're all transferring over from the lithium to the chlorine. All right, so we talked about that. So talking about bond energy, when we talk about energy, and we'll talk a little bit about it here, even though we're not supposed to talk too much about energy in this class, but we'll talk a little bit about bond energy as it relates to bond making and bond breaking. So one way that we represent energy in reactions is through delta H, which is the change in enthalpy, which again is a fancy way of saying basically the heat or energy of a reaction. So when we break bonds, that is all endothermic processes, which means heated energy needs to be put in to do so. So if you have a bond together and you put energy in, everybody gains energy and they're able to sort of wiggle away from each other and break apart from one another. Actually, when we make bonds, it's an exothermic process. You got everybody away from each other. As they lose energy, they kind of slow down and they allow themselves to now be able to come together and form a bond. When we do a chemical reaction, pretty much the only thing that happens is on the reactant side to the product side, we pretty much break all these bonds. And then we make all these new bonds basically on this side. And one way that we calculate the change in enthalpy for a system is usually products minus reactants. So our delta H of the reaction would be the delta H of all the products in this case, minus the delta H of all the reactants. So if you were to calculate the delta H of this reaction based on bond energy or bond enthalpy, it's sometimes referred to, you basically would add up all the bonds you broke on the reactant side and then add up all the bonds you made on the product side. And you basically add them together, making sure that one's exothermic and one's endothermic, remembering that if it is endothermic, the delta H values are positive. And if it's exothermic, where heat and energy is released, delta H value is negative values. So you basically need to keep track of everything that you broke, everything that you made. And by track of that, you need to know, is it a single bond? Is it a double bond? Is it a triple bond? It takes different amount of energies to break single, double, or triple bonds. And you also got to keep accounting of, how many you broke and how many you made along the way. So there is a table where you could do that looks something like this. And this gives you the delta H values for all of these bonds here that you make and break. So for example, let's say we wanted to calculate the delta H of this reaction here. So we'll do our, draw it here, I think. So we have the table. So we have CH4, Cl2 goes to that should be HCl. HCl. There you go. All right. So why don't you do that? So we want to add up everything that we're going to break on the left-hand side. And then all the bonds that we make on the right-hand side. Again, the ones that we make should be exothermic, negative. The ones we break should be positive. And then add them together and see what you get. So take a minute or two and see what you come up with. Take a look together here on this one and see if you're on the right track. So basically in this situation, if you're not sure, you should draw the Lewis structures, which is very badly drawn here. So we'll redraw them here. And you really want to make sure you draw the Lewis structures if you're not sure what things look like. And you may just want to draw them so you can visually see all the bonds that are being made and broken so you don't miss any along the way. All right, so basically on the left-hand side here, we need to break all the bonds that we see. So if we just sort of add up what we need to break, we clearly need to break 1, 2, 3, and 4 carbon-hydrogen single bonds. So we're going to break 4 carbon-hydrogen single bonds. And if we go to our table, the carbon-hydrogen single bond was 436 kilojoules of energy. We also need to break 1 chlorine-chlorine single bond, which is right there. And if you go to your table for chlorine single bond, that is 243 kilojoules. I believe that is all the breaking we will be doing here today. So if we add up all that good stuff, that's going to be 4 times 436 plus basically 243 gives us 1987 kilojoules of energy to break all the bonds. This is a endothermic process because energy needs to be put in to break the bonds. So it is going to be a positive here. 1987 kilojoules. Any questions on that there? Now on the other side, we need to make all of our bonds. So on the other side there, we're going to make, not that, we're going to make, it looks like 1, 2, and 3 carbon hydrogen bonds. So we're going to make 3 of those guys. So 3 of our carbon hydrogen single bonds, each at 436. We're also going to make 1 carbon chlorine single bond at 339 kilojoules. And we need to make 1 hydrogen chlorine single bond at 431 kilojoules, right? So we're going to add up all that together. That gets us 3 times 436 plus 339 plus a 431 gets us a 2078 kilojoules. Now, because making is a exothermic process, basically all these numbers here are negative, giving us a negative value for this guy. Any questions on that? Yeah. You would, yes. You're not going to memorize the table? That is the test. It's just going to be the table. You put in the kilojoules. Now, everybody could go that way to drop now. Now you would have the table. At this point, once we've adjusted the signs, we could get the delta H of the reaction by simply just adding the numbers. That would give us a plus 1987 plus a negative 2078 kilojoules, going to give us 1987 minus 2078, basically. Gonna say negative 91 kilojoules in this case. Overall, this reaction is endothermic or exothermic? It is exothermic. We ended up with a negative delta H here based on bond energy. Any questions on that? Variation of this calculation is sometimes people will go, you broke 4 bonds on the left, but made the same 3 bonds on the right. So that's a net difference of 1. So you could do that as well for like the carbon hydrogen sort of move. Yeah, so I mean, I personally think you should draw it and go each bond individually so you don't miss any, but some people in some books will go, hey, we broke 4, made 3 of the same. So that's a net difference of just breaking 1. You could do that and it would come out the same. Yeah. Other questions on that? All right, so why don't you try a couple here now that you're professionals, I suppose. I'll put the table up there since apparently you haven't memorized it. All right. I showed it to you for like 30 seconds. You didn't get it all. I made you sad. All right, so we'll do, how about N2 plus H2 makes some NH3. And we'll do a little balancing there like we're chemists-ish. Let's take a look. So again, I would highly recommend that if you're not 100% sure of what these things look like, you just quickly kind of sketch it so that you make sure you have the right bonds. And also, like I said, sometimes visually just seeing the Lewis structures helps you not miss bonds. It's very common sometimes people focus like on the outside bonds, and if there happens to be like a center bond between 2 atoms, they kind of miss it a lot. So just visually seeing it sometimes is very helpful. So as we I think drew last time, we had our nitrogen, which should be a triple bond action happening there, plus 3 of our hydrogen, which is single bonded. And that's going to go to 2 of our NH3s, right? Looks something like that, I think, if I did that right there. All right, so this means the coefficient that we actually have that going on, right? And this coefficient means we actually have that going on, which again is another very common mistake that people make. They just kind of do the one Lewis structure, ignoring the coefficient, because then you have a couple of other molecules happening. So now we're ready to break and make here. We're going to break, obviously, here one nitrogen triple bond, which is important that you did not get single or double there. That's a 946, I believe. In this case, we're actually going to break 3 hydrogen single bonds, one in each of these guys here. And each of those guys are about a 436er. And I think that is all we're breaking there. So that's going to get us 3 times 436 plus a 946. That looks like a 2254 kilojoules. Once again, breaking is endothermic, so it will be positive. On our making side, we're going to make 1, 2, 3, 4, 5, and 6 nitrogen hydrogen bonds. Each is 389, I think. And it really will be negative since it is making. And I believe that is it on that. So 6 times 389 gets us a negative 2334 kilojoules. That means our delta H of this reaction based on bond enthalpy or energy would be 2254 plus a negative 2334 kilojoules. Gets you negative 80 kilojoules in this case, yes. Also exothermic based off of bond energy. Any questions on that there? So the key where people screw up the most on this is a couple of things. Like I said, not really understanding what bonds they're dealing with. So they just grab like the first right letters on the table. So you got to make sure you know if it's double, single, or triple. Secondly, like I said, they visually miss some bonds. So seeing it is helpful, and negative and positive exothermic, endothermic. No, so the 2 really does mean you have 2 molecules of them flying around. So they're not together. Yeah, if they were together, you would have a bond that would bind them together, and then that would be an extra bond you would have to add. So I think what you're asking is this, and if I'm not, then let me know. But I think you're asking, is it like, they're together like this? And the answer is no in that case. The 2 just means we have 2 separate ones. If you had something like this, then if we were doing this guy, this is like I was talking about before. If you had something like this, it's very common. People get all the outside ones, but always miss like the middle one there. So again, visually drawing it, you can see it. But to answer your question, no, that basically means they're separated on that last one. Other questions on that there? All right, well, I'm going to lay it up there.